Okay, so we're going to look at this RL series circuit. So your resistor value there is 82 ohms. Your inductor value there is 250 millihenries, so 250 times 10 to the minus 3. To work out what your total impedance is, you need to work out what impedance is due to the resistance. And the impedance due to the resistance is just the value of the resistor, that 82 ohms. And you also need to know what the impedance is due to that inductor. And if you remember from last week, the impedance due to an inductor, will say that ZL is XL. So that's the number of ohms that you get because of that inductor. And XL is 2 pi FL. So 2 and pi are just numbers. F is the frequency of the supply, that 50 Hertz. And L is the value of that inductor. So that's 250 times 10 to the minus 3 for the milli. So in your calculator, I didn't do a recording last week. Just did it on the board. So that's 78.54 ohms to 4 significant figures. So 4 significant figures, so I can round my final answer to 3. From the rules that we wrote down last week, that in rectangular form is J78.54, and in polar form, yes, 50 for that frequency of supply. That's where that 50 comes from. So that's what that XL is as a rectangular number and as a polar number. So that's in its two forms of being complex numbers. Your impedance of your resistor is just the value of the resistance, that 82 ohms. Now that, as a rectangular number, is 82 plus J0 if you like, or 82 at an angle of 0. These are all in ohms. Yeah. So I've went for ZL being the impedance of the inductor, ZR being the impedance of the resistor. Zero. Because resistors are just real. So then in the same way as if it was a DC circuit, and I was asking you to add up two impedances, you would just add them up. You're going to do the same kind of thing for your Z total, but you're going to add them up as complex numbers. So you're going to add up the impedance of the resistor, and you're going to add on to that the impedance of that inductor. So you're going to add those two together. Because you're adding, you want to be in rectangular form. So you want to add and subtract in rectangular form and multiply and divide in polar form. So you want to add and subtract in rectangular, and you want to multiply and divide in polar. That's the easiest way. So because we're adding and subtracting, we're going to be in rectangular form. So we're going to add our ZR, which is just 82, is J0, so we can just leave that out. We're going to add on our J78.54. So you've really got your 82 coming from here, and your J78.54 coming from there. Now your final answer should all be in polar form, so you're going to convert that from rectangular to polar form. So in your calculator, usually it's shift pole. then 82, 78.54. And that'll be your conversion. So it gives you an R, which is the magnitude, sticking to 4 significant figures, and an angle, which will be a positive angle, 43.77. And that's ohms. So the value that you've got now from converting that rectangular number there into this polar number here, that's the value for the total impedance in the circuit. So I've called it ZT. That's the total circuit impedance. So if you think about it, that'd be the way you'd usually start a DC circuit, where you'd work out what the total resistance is. You're doing total impedance. And that's your kind of first thing. Then moving on from that, once you've done your total resistance, you'd usually do your total current. We're going to do the same kind of thing again. So you're going to go from that to doing your total current. So from what we know before, I used to be equal to V over R. So we're in an AC circuit now, so I equals V over Z. So your voltage is 100 volts there. They're not giving you an angle. Where they don't give you an angle, you take that to be the reference and you make the angle 0. So if there's no angle there, you make the angle 0. And then you're going to divide that by your Z. Because you're going to divide, you're looking up here, multiply and divide in polar form. We're looking for an impedance in polar form, which is that value there. That's just my page. And when you're dividing these polar numbers, you divide the magnitudes, you subtract the angles. So you're going to do 100 divided by that 113.5. 0.8811 if I'm sticking to my 4 significant figures. And my angle 0 minus 43.77 is just minus 43.77. And that's in amps. And that's your supply current. So if you're adding that onto your diagram, it would go in there. When you're looking at these angles and these angles are positive or negative, it shows you whether or not your circuit's inductive or capacitive. So if you had a capacitive circuit rather than an inductive circuit, that angle would be negative and that angle would be positive. It'd be the other way around. No, we're going to draw impedance phasor diagrams and phasor diagrams after this. Hopefully that will kind of make a bit more sense. So now we've got our total impedance, which is our total ohms in the circuit. We've got our current in the circuit. So what you'd usually do now if it was a DC circuit is you'd work out the voltage across each component. We're going to do the same thing. So we're going to get the voltage across the resistor. V equals I times R. And because we're multiplying, we want to be in polar form. So my resistor in polar form is that value there, that 82 at an angle of 0 degrees. That's been a wee bit blurry, I think. Right, so let's have a look at this. So you're going to do 0.8811 and multiply that by 82. To fourth significant figure, 72.25. And my angle, minus 43.77 plus 0, stays the same, minus 43.77. Then my VL will be I times XL. So the same current, and my XL is a polar numbers up here, 78.54 at an angle of 90. Multiply the magnitudes. $69.20 if you're sticking to your four significant figures. And then you're going to add your two angles there. So that gets you going from a negative to going to a positive, 46.23. Now usually, if this was a DC circuit, you would just add these two up and you'd say, well, these two added up gets you that number there. It's correct, that's all fine. Because these are done as phasors, we don't really know if these two add up to get us this. We can check by converting these into rectangular numbers, or we can draw the phasor diagram and check from that. So I'm going to draw the phasor diagram and check from that. So there's two diagrams you can draw for this. You can draw your impedance diagram, and when you draw your impedance diagram, the things that you put on it are your ZL, your ZR, your Z total. And in your impedance diagram, the things you put on that are your VS, your VR, your VL, and your I. So we will do a phasor diagram. So if you've got a protractor, that's great. And if you don't, you'll have to just kind of go for your best estimate. So the values that you want when you go and you do your actual phasor diagram would be your supply voltage, which we had been as 100 at an angle of 0. Your voltage across your resistor. In fact, if you don't have a protractor, it might be a good idea to convert these into rectangular form and then you can plot them. If you've got squared paper, I've got squared paper that you can use. Your VL. And your current I. Now you have to choose a scale for your voltage and a scale for your current. Obviously they won't be both the same scale because your voltages are usually large and your currents are usually small. So that's something to consider. So for my current scale, I'm going to say 1 centimetre equals 0.2 of an amp. So my current is 0.8811 divided by 0.2 is giving me 4.4 centimetres. And it's at that angle, that minus 43.7. If you draw it, you can check it. Yeah. And also you can be asked to draw them just as a normal question. Yeah. Yeah. Because it's not as straightforward as in a DC circuit where you can just look and add them up and check. You'd need to either convert them into rectangular rectangular form and add them up to check, or draw your phasor diagram. I quite like the phasor diagram because it kind of gives you exactly, and that kind of suits my brain. So that's my current phasor down there. Help yourself. No, because you could just add them. We'll do that as well. We'll do that afterwards. And we'll show you both. Let's see if I've got a pen. No, you're fine. So let's see if I get a pen that's not. So if you were going to convert these into rectangular form, so this is rectangular form, you'd convert that. So you go shift into rectangular form, 0.8811, comma, minus 43.77. So that would be 0.6363 minus J 0.6095. So that would be that as rectangular form. So if you were plotting that and you said, well, 1 centimetre is 0.2 of an amp, that'd be 0.2, 0.4, 0.6, 0.63, be about here, minus J, 0.2, 0.4, 0.6095, a wee bit over. And that kind of pretty much does tie in with that point there. So you do the same if you were doing for your VR and your VL, but I'm going to do that algebraically on the other page. So I'll do it as a phasor on this page and I'll do it algebraically as well. So pick a scale for your voltages. 1 centimetre equals 25 volts, say. So my VS, 100 at an angle of 0. That'll be 4 centimetres. Then my VR, it's got the same angle as my current has, so I can just use that same phasor, 72.25. 72.25 divided by 25, 2.89 centimetres. It's about there. That's my VR. My VL is going in the positive direction, so I measure my angle upwards, up this way, 69.2. It's my 2.77 centimetres. It's about there. And similarly that, on the end of that, as in a phasor addition of those two, gives you your VS. So your VR plus your VL, so I've taken that and put it on the end of there, gives you your VS. So that proves the phasor addition of those two phasors gives you that VS. So when you add VR plus VL as phasors, this is the current converted from polar to rectangular. So going from polar to rectangular is 0.6363 minus j 0.6095. It is a wee bit blurry. So that would be your phasor diagram. And if we go back and check it again, looking at our values of VR and VL, so if I convert these two values here into the rectangular form, so going into rectangular form, you go shift rec, gets you 52.17 minus G 49.98. And for your other one, $47.87 plus J. So if you add your VR and your VL with these rectangular numbers, add the real parts, that's all right. I've just converted these into rectangular form. That's fine. And then you can see that pretty much, when you convert that into polar form, $100.0 if you're going to 4 significant figures and sticking to that, angle minus 5.7272. But pretty much one checks the other. So if you convert them back into rectangular form and add them up, you'll get your supply voltage, or you can use our phasor diagram and do the same thing.